Okay, picking it up. Moving ahead. It's the mean value theorem. We're ready. The mean value theorem, abbreviated MVT, sometimes affectionately referred to as the most valuable theorem. It's not the most valuable theorem at all, but it's fun to say that sometimes. MVT, okay, what is the mean value theorem? So it turns out this is in a way a simpler, more general version of Rolle's theorem. Okay, if f of x satisfies the two hypotheses, so we're trimming it down. So it turns out we're only gonna keep the first two hypotheses from Rolle's theorem. Number one, that f of x is continuous on the interval a to b. And number two, that f of x is differentiable on that interval from a to b. If just those two are satisfied, we can still make a conclusion. Then there exists c in ab such that f prime of c will equal this, f of a minus f of b over b minus a. Okay, what's going on there? What does that equal to, right? So you think, all right, so the interval is a to b. What is this? This is the slope between the points at a and b, right? y2 minus y1, x2 minus x1. That is the slope of the line. If you were to, graph it and draw a line connecting the endpoints, that would be the slope of the line between the endpoints. Interesting. So we're saying if you're continuous and you're differentiable, we don't care about where the y values of the endpoints are. We got rid of that hypothesis, so they don't have to equal each other anymore. There exists c where the derivative now is equal to this slope, not zero any longer. Okay, so like I said, a more general version. Let's take a look at some drawings and then even kind of see how it connects. Why is Rolle's theorem, a more specific version of the mean value theorem? Okay, so my first drawing here is the simpler drawing. So we've got, a function from a to b. The y values of the endpoints don't have to equal each other now, so they can be different. But it does have to be continuous and differentiable, and that's what we see there. All right, so what's the deal with this, the slope of the line between the endpoints, right? So if we draw that line between the endpoints here, what we're saying is somewhere between a and b, there's a point whose tangent line will be parallel to this line. It will have the same slope. There's a point whose tangent line has the same slope as that. And you think, okay, so kind of on that bump, kind of in here, right? If you kind of tilt your head, right? It's kind of right in there somewhere. There would be a point where the tangent line would have the same slope as that line connecting the endpoints, again, parallel. Yeah, I guess that's true. Why do we call this the mean value theorem? It's actually from the slope connecting those endpoints. If we know the slope connecting the endpoints, that is the average slope of f of x on that interval from a to b. So when we say the mean value theorem, we mean the average. What's the average slope value? What's the average of all the rates of change, right? So if it begins here and it ends here, right? So as we look, sometimes the slopes are pretty steep, but sometimes they're not. Well, if you took the slope at every single point, there's infinitely many points, but if you took the average of all those slopes of the tangent lines, they would work out to the slope of the line connecting the endpoints, because that's your beginning and your end. And so at some point, if that's the average, at some point there must have been a place where the slope of the function, right, the slope of the tangent line was equal to that average. It has to happen at least once, right? If on average you're doing something and you're continuous and you're differentiable, then at least one time you had to equal that average. There's kind of a similarity between the mean value theorem and the intermediate value theorem. You remember that one? So in the intermediate value theorem, we'd set up the examples where the function, whatever we thought of as the function, was equal to 0. We'd plug in the x values of the endpoints, and we get one to be positive, one to be negative. And we'd say, well, if it started positive and it ended negative, at some point it had to pass through 0. That's kind of similar. There's kind of a similarity here. If this is the average, then at some point in between, it had to equal the average at least once. And the average, though, that's where we get the name mean value theorem. Okay, let's look at the next drawing. A little bit more going on here. We say, okay, right, maybe the A is the higher Y value and the B is the lesser, and it goes up and down and back up. And okay, well, if you just draw that line connecting the endpoints, then we know at least one time, but perhaps more, the slope of the tangent line was parallel to that. And yeah, it happens 3 times here. So, kind of roughly C1, C2, and C3, the mean value theorem guarantees that it has to happen at least once. There you go. Okay. Let's check out this example. Kind of a similar one to what we just saw. Does f of x satisfy the mean value theorem on the interval? If it does, find all the c values that satisfy the conclusion of the theorem, where there's at least one c that's equal to the same slope as the slope connecting the endpoints. Okay, and we're going to do it, hopefully this works, we're going to do it for f of x equals x cubed minus 2x plus 6 on the interval from -1 to 3. All right. Does f of x satisfy the mean value theorem on the interval? If so, find the c value. Okay, and we had f of x equals x cubed minus 2x plus 6 from -1 to 3. Okay, so first thing we gotta do, we gotta check just the 2 hypotheses. Number 1, is f of x continuous on -1 to 3? Well, here we just have a polynomial again. Yep, no holes, no jumps, no vertical asymptotes. Okay, is f of x differentiable? On -1 to 3. So we'll take a look at the derivative, but don't think anything unusual is going to be going on. There it is, 3x squared minus 2. Yep, there's no division by 0, anything funny happening. All right, great. So this satisfies the mean value theorem. That's part of our answer. Okay, now find c. What we'll do, let me actually just write the conclusion of the theorem, right? F prime c equals f of b. Kind of remind ourselves what that formula was. That's the conclusion. All right. So we know what the derivative is. We're going to take 3x squared minus 2 and plug it in, just make that the left side. The right side, we're going to have to do some calculations. We'll say, okay, 3x squared minus 2 equals, our interval was -1 to 3. So we'll say, okay, this is f of 3 minus f of -1 over 3 minus -1. Let's figure out what this number is. Once we get this number, then we can solve for x and we'll have it. Let's see, f of 3. Plugging f of 3 in. 3 cubed is 27 minus 2 times 3 is 6, but then plus 6, that's going to be 27. Okay. Minus -1. -1 cubed is -1, plus 2 is +1, plus 6 is 7. Okay. And we're going to divide by 4. So we got, let's just get it here. We got 20 divided by 4 is 5. All right. Now, if we solve for x, we'll have it. Not too bad. We can just add, divide by 3, square root, make sure there's a plus or minus there. Okay. Now, at least one of these has got to be in our interval. Let's see. X equals the positive square root and x equals the negative square root. They might both be. I don't really know what these numbers are, so I'm going to grab my calculator. Square root of 7/3. Okay, I got 1.53. So this one would have to be negative 1.53. Ah, you know what? This one, the negative version is not in the interval. Only this one is. So that's our only C, right? We're calling it X, but that's the only time, the only X value, the only location where the slope of the tangent line is equal to the slope between the endpoints. Hey, what if, so we got the answer. Let me just give this follow-up question. What is the slope of the tangent line in question here? Like, what is the slope between the endpoints? And what is the slope of the tangent line that's parallel to it? Turns out we did find it in our work, although we didn't really point it out at the time. What is the slope between those endpoints? The average slope of the function on our interval. So if you kind of look back, you're like, well, it was this right here, and then we did it, and there it was. It was the 5. That was the slope between the endpoints, if you're curious. And so at this moment, we've got the tangent line has the same slope of 5 right there. So if we were to plug this into the derivative, right, then we would also get 5. And yeah, that makes sense, right? Plug it in, it would be squared. So it'd be 3 times 7/3, 3's would cancel, 7 minus 2, yeah, would give us the 5. Same true here, but this point just doesn't happen to be in the interval in question, so we can ignore that. All right, a lot of fun, you guys. We've got a couple more examples where we go take a little bit different perspective on mean value theorem. That's next.